Hello and welcome to our Precalculus Practice Midterm Exam. First, notice that it says you must show your work for every problem in order to receive credit for your correct answers. And so we're going to run through the problems showing the work needed in order to receive credit. Starting with number 1, they want us to find the domain of the function. We need to give our answer in both set and interval notation. So the first thing you need to notice is that our function is a square root function, and in order to find the domain, you first have to find the restriction. So for a square root function, we know the restriction says that the radicand must be greater than or equal to 0, and then we need to solve for x. So I'm going to move the 14 to the other side, which will give us negative 2x is greater than or equal to negative 14, and then divide both sides by negative 2. Now remember, when you divide both sides of an inequality by a negative number, the inequality flips, and we're going to end up with x is less than or equal to 7. The set notation from here is super easy. All you have to do is add a few bells and whistles. We need a brace, an x, a vertical bar, and another brace. And so this says the set of all x such that x is less than or equal to 7. This would be our set notation. And then for the interval notation, since x must be less than 7, it's going to go all the way back to negative infinity. Numbers that are less than but equal to 7 means that the 7 is included, and so we're going to use a bracket. And then this would be your interval notation for the domain. Next, number 2. Again, we need to find the domain of the function given in both set and interval notation. This time you need to notice that you do have a rational function, and the restriction says that the denominator cannot be equal to 0. That is the restriction. Then you need to solve for x. Moving the 21 over makes it positive. Divide both sides by 2. And now we know what x cannot equal. Guess what? X can be anything else except 21 halves. So again, the set notation is pretty easy. We're going to need a brace and a variable, and a vertical bar and a brace. So again, this says the set of all x such that x cannot be 21 halves. The interval notation, again, remember x can be anything, any real number, except for 21 halves. So we would say that x can be anything from negative infinity up to 21 halves, not including 21 halves. Skip over to the other side of 21 halves and keep going. This is your interval notation for that domain. Next, number 3, find the difference quotient. Well, the first thing you need to know is what is the formula for the difference quotient. That is f of x plus h minus f of x all over h. And here the first piece of the puzzle that we need to find is f of x plus h. So to find f of x plus h, we're going to replace every x in f of x with x plus h, and then we're going to need to simplify that expression. So x plus h squared means x plus h times itself, and that's going to require the FOIL method. The negative 7 needs to distribute, and then let's FOIL. X times x, x times h. On the inside, we have another x times h, and h times h. Minus 7x minus 7h. Remember, we're working on the first piece, f of x plus h. We need to combine like terms. That's going to give us x squared plus 2xh plus h squared minus 7x minus 7h. And that finishes the simplification for f of x plus h. Now for the rest of the difference quotient, we need to add minus f of x all over h. And this is where we begin the actual difference quotient. So this negative needs to distribute. That's going to give me a negative x squared, which will cancel out the positive x squared. Here the negative and the negative, that'll make that a plus 7x. That will cancel the minus 7x. And then this fraction is going to simplify to 2xh plus h squared minus 7h all over h. And then notice that every term in the numerator has an h. So then we could factor out an h, leaving me 2x plus h minus 7 all over h, and then we can cancel our common factor. So here the final answer for the difference quotient would be 2x plus h minus 7. Next problem, number 4. Use the graph of the function shown to answer the following questions. And the first thing they want us to find is f of 2.2. So we want to know if x is 2.2, what is y? And so we're going to go to where we have an x coordinate of 2.2, and then we need the y. That would equal 3.9. And do you see there is basically no work to show here? You just have to know what to look for. Part B, for what values of x is f of x, remember that's y, equal to 5? And so now we need to go to where y is 5 and find all of the x's that have a y value of 5. Well, here's one of them. So one of the values here would be negative 8. But if we scan across at a height of 5, do you see that the graph has another ordered pair that's going to be at a height of 5? There is another ordered pair with a y value of 5, and it appears that that x is going to be right here. 1, 2, 3, 4, 5, 6. It appears that that is going to be at 6. So again, there are two x values that have a y coordinate of 5 on this graph. Part C. What is or are the x-intercepts? We need to find every point where the graph touches or crosses the x-axis. And we know that x-intercepts will have a y coordinate of 0. So our first x-intercept appears to be negative 9.5. Our next x-intercept would be at negative 5. Next, we have an x-intercept at 0 at the origin. We have another x-intercept at 4. And then notice we do have another x-intercept here that's not labeled. So we're going to have to estimate where that is. If we count over 1, 2, 3, 4, 5, that's a little bit more than 5. In fact, almost to 6. So we might call that 5.5, 5.8. Anything within 5 to 6 should be a pretty good estimate. And then once we have all of the x-intercepts identified, we need to write them as ordered pairs. So we're going to have negative 9.5, comma 0, negative 5, comma 0, 0, comma 0, 4, 0, and finally 5.8, 0. Next, what is the y-intercept? Where does the graph intersect the y-axis? At the origin. And again, we need to record that as an ordered pair. What is the domain? Well, this graph appears to continue infinitely far in both directions. So we would say that the domain is all real numbers. In interval notation, that would be negative infinity to infinity. The range also appears to go up forever and down forever. And so the range, again, in interval notation would be everything from negative infinity to infinity. It is important to remind you that the domain and the range have to be recorded from the negative to the positive. Next, number 5, we need to find the average rate of change from 4 to 6. And that means you need the formula for average rate of change. That is f of x2 minus f of x1 divided by x2 minus x1. Now, it doesn't matter which one of these numbers you designate as x1, but I'm just going to choose the first one to be x1. And so 6 would be x2. And then we need to plug into the average rate of change formula. In the numerator, we're going to have to evaluate the function at 6 first. So that will give me 6 squared minus 5 times 6 plus 12. The formula then has a minus. And then we need to evaluate the function at 4. So that would be 4 squared minus 5 times 4 plus 12. And that is all over 6 minus 4. And this would be a great time to use your calculator to input that all at one time. I'm going to show the steps. 6 squared is 36. 5 times 6 is 30 plus 12. 4 squared is 16, and I am going to distribute that negative as I go, plus 20 minus 12, all over 6 minus 4, which is 2. And then to simplify, plus 12 minus 12 cancel. 36 minus 30 is 6. Negative 16 plus 20 is 4. 6 and 4 is 10. 10 over 2 is 5. Number 6, determine the quadratic function with a vertex of 4, negative 1 and passing through this other ordered pair. Notice it does say to write the function in vertex form and standard form. Okay, so since they gave me the vertex, we're going to start with vertex form, which is a formula you need to know. That is ax minus h squared plus k. The vertex is the ordered pair h comma k. And notice that this other ordered pair that they gave me is just a generic x and y on the graph. So we're going to be able to plug in for 1, 2, 3, 4 of these pieces, and then we can solve for the one piece we don't know, which is a. All right, here we go. Remember, f of x is y, and I do have a generic y, which is negative 4. A, we don't know. X comes from the generic ordered pair. X is 3. H comes from the vertex. And so does K. And now we can solve for A. Okay, so adding 1 to both sides gives us negative 3. 3 minus 4 is negative 1. But negative 1 squared is 1. 1 times A is A. And so there we have our value for A. And now we can answer the problem in vertex form. The function would be f of x equals a x minus h plus k. And notice I plugged in for h and k as I went along. And there is our function, that is the quadratic function, in vertex form. Now to get standard form, we just need to, well, multiply that out. So we're going to have negative 3x minus 4 squared means that we're going to need to FOIL it. So the negative 3 comes down, and then we need to FOIL. X times x times negative 4. Another negative 4x. And last but not least, we have a plus 16 minus 1. And then I'm going to distribute the negative 3 and combine like terms all at one time. Here we go. Negative 3x squared. Negative 3 times negative 4 is positive 12. And I'll have another one just like it. 12 and 12 is 24x. Negative 3 times 16 is negative 48. Minus 1 would give us a negative 49. And there is our function in both vertex form and standard form. Next problem, number 7. For the quadratic function, answer the following questions. First, does the parabola open up or down? Well, we can see that a is negative 1, and if a is less than 0, the parabola opens down. Next, determine the vertex, which means we need the ordered pair h comma k. And to find h, we have a formula, minus b over 2a, which we can see that b is negative 2. So that's going to be minus a negative 2 all over 2 times negative 1. Simplify all of those negatives. That's going to give us a negative 2 over 2, which is 1. And there is the x coordinate of the vertex. Now to get k, you simply find f of h, which is f of negative 1, which means we need to plug that into the function and simplify. So we're going to have minus negative 1 squared minus 2 times negative 1 plus 15. And this would be a fantastic time to make use of our calculator. So we're going to have minus negative 1 squared minus 2 times negative 1 plus 15. And our y-coordinate of the vertex is 16. So as an ordered pair, the vertex would be negative 1, 16. Next, determine the axis of symmetry. Remember, that has to be an equation, so you have to have an x equal, and that is always x equal h, which is negative 1. Determine the x-intercepts. That means we need to set our function equal to 0 and solve. Okay, so if we set our quadratic function equal to 0 and solve, the first thing that I'm going to need to do is divide both sides by a negative or multiply both sides by a negative. Either way, that's going to change all the signs. And now I have a trinomial in standard form. Let's try to solve by factoring. The signs are going to be different. X and x make x squared. And I need numbers that multiply to make 15. That's subtract and make 2. And I believe those are 5 and 3. Okay, so setting each factor equal to 0 and solving for x, we're going to get x is negative 5. And we're going to get x is 3. And we do need to write those intercepts as ordered pairs. So negative 5 comma 0 and 3 comma 0. Next, determine the y-intercept as an ordered pair. If we go back up to the function, the y-intercept is always at the constant. And so our y-intercept would be 0, 15. And finally, we get to graph the function by plotting all the points we have so far. So we have a vertex of negative 1, 16, which is going to be off of my chart. 11, 12, 13, 14, 15, 16. Negative 1, 16 is going to be about here. X-intercepts of negative 5 and 3. A y-intercept of 15, which is going to be about here. And then we can draw our parabola. There you go, something like that. Now that we have the graph, it should be pretty easy to get the domain. Actually, the graph is not even needed for the domain, since we know that the domain of any polynomial, here we have a quadratic, is always all real numbers. And this is in interval notation here. If you want to write that in set notation, that would be the set of all x, such that x is an element of the reals. And so that is the fancy math notation for set notation. Next, we need to determine the range in both set and interval notation. Probably the easiest way to do this would be interval notation first. Did you notice that the highest point on this graph is 16? And then the graph goes down forever. So the interval notation for the range here would be everything from minus infinity up to 16, where 16 is included because the graph does actually exist at 16. That's where the vertex is. Also notice that the interval notation has to be from bottom to top, so that's why we went minus infinity up to 16. And then for the set notation, that would be the set of all y, because the range are the values that y can be, such that y is less than or equal to 16. Notice that this graph will include every y value from 16 and below, everything less than or equal to 16. And I think the last thing we have to do here is to determine the intervals where the function is increasing and decreasing. And so if we look at our parabola and maybe sketch in the axis of symmetry, remember that that axis of symmetry was at x equal negative 1. We can see that this graph is increasing from negative infinity up to that value, and then it is decreasing from negative 1 to infinity. So if you have the graph, the increasing and decreasing should be pretty easy. Okay, so here we have increasing from negative infinity to negative 1. By the way, you do always use the value from the axis of symmetry. And the decreasing would be everything from negative 1 to infinity. There are those answers right there. Next, number 8, a projectile is fired from a cliff 12 meters above the water with an initial velocity of 179 meters per second. The height of the projectile above the water in meters is given by this function. So that is important. Where t is the amount of time in seconds after the projectile was fired. We need to use this information to answer the questions. First question, when will the projectile reach its maximum height? Well, if you notice, this is quadratic, where a is negative, and so that's going to indicate a parabola that opens down. We know that the maximum height will occur at the vertex. So when it says when will it, that means we're looking for time. Notice time is the x coordinate or the x variable. And so we're going to be looking for the value of h from our vertex. We know that h is negative b over 2a, which in this case b is 179. So that would be minus 179 over 2a, which is negative 9.8. And then if we work that out with our calculator as a fraction, we have negative 179 over 2 times negative 9.8 and equals. And I believe it wants that rounded to the nearest hundredth, which is 2 decimal places. And so we need to hit the SD button. That would be 9.13. 9.13 seconds after the projectile is fired, it will be at its maximum height. Part B, what is the maximum height? Well, that would be the k coordinate of the vertex. And remember, to find k, you need to evaluate f of h. Okay, but in our function, that is h of the time. So instead of f of h, that's going to be h of 9.13. And then plugging into our function, negative 9.8 times 9.13 squared plus 179 times 9.13 plus 12. And then if we input all of that into the calculator all at one time, we're going to have the maximum height of the projectile. So here we go. Plugging that in, we're going to have negative 9.8 times 9.13 squared plus 179 times 9.13 plus 12. And our maximum height, notice it says rounded to the nearest hundredth, would be 829.37 meters. Remember, that is the height here measured in meters. And then finally, they want to know, at what time will the projectile hit the water? So then I've got a question for you. When the projectile hits the water, how high will it be above the water? Well, it would be 0 meters above the water. When it hits the water, it's going to be at the water level, so the height would be 0. So to answer this question, we're going to have to set our function equal to 0 and solve. So 0 equals negative 9.8 t squared plus 179t plus 12. And one of the ways we can solve a quadratic is with the quadratic formula. Now the value of a, if you're going to plug and play, does need to be positive. So let's multiply through by negative 1. That's simply going to change all the signs. And then we can see our values for a, b, and c. And then we can plug into the quadratic formula. Here we go. T is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then from here, we're going to plug that into the calculator, doing the plus and the minus separately. All right, so first thing I notice is that a negative and a negative here make a plus, so I'm going to go ahead and make that a plus. As a fraction, that would be 179. We're doing the plus first, plus the square root of, parentheses, negative 179 quantity squared, minus 4 times 9.8 times negative 12. Notice I can just use the time symbol in the calculator rather than parentheses. But if you want to use the parentheses like I have it written, that would work too. In the denominator, 2 times 9.8, and that's going to be 18.33. Again, we need that rounded to the nearest hundredth. 18.33, that would be seconds. Now, going back to the calculator, we can actually just edit what we input before. That is, if you have the class whiz, you can scroll back to where you have the plus. You can hit delete and insert a minus. Oh, and that's going to give us a negative number. Does negative time make any sense in this problem? No. And so that solution is extraneous. That solution has no bearing on our problem. And so this is the value we're looking for. This is how long it will take the projectile from the time that it is fired till it hits the water. Next, number 9, we have an exponential equation to solve. We are going to use the method of common bases. So notice here I've got 6 raised to the power x squared minus 63. On the other side, I have a 36. We know that 6 squared is 36. And now if you notice, I have a common base. Both bases are base 6. So the 6 squared is also raised to the x. Anytime you have an exponent raised to another exponent, that's when you multiply exponents, which would give me 6 to the x squared minus 63 equals 6 to the 2x. And when you're doing the method of common bases, once the bases match, they cancel, and the exponents become your new equation. So here we can see that our exponential equation has now become quadratic, which means we need to set it equal to 0 and solve. And that's going to give me x squared minus 2x minus 63 equals 0. And the fastest way to solve a quadratic is factoring, if it will factor. So here if I read the signs, they're going to be different. X and x to make x squared. And are there numbers that multiply to make 63 that subtract and make 2? And I believe those numbers are 7 and 9. The 9 does have to go with the minus so that we get negative 2. And then I can set each factor equal to 0 and solve. Moving those numbers over is going to give me x equal negative 7 and positive 9. And if we plug those back in to check them, you will find that they both work. And so those are the solutions for that equation. Next, number 10, we need to solve the equation. Notice it wants us to give the exact and the approximate solutions. The approximate solution needs to be rounded to 3 decimal places. So we have another exponential equation. The first step here would be to isolate the exponential. So bringing the negative 7 over makes it a positive, giving me e to the 8x minus 5 equals 25. And now that we have the exponential isolated, we know that to get rid of a base of e, we need to take the natural log. But whatever I do to one side, I have to do to the other. So we're going to take the natural log of the other side also. And then we can use the properties of logarithms. So remember, the power rule says if you're taking the log of something with an exponent, that exponent can come down and be the coefficient, and natural log of e is 1. So that's going to leave me only 8x minus 5, because 1 times anything is itself. On the other side, we still have natural log of 25, and it looks like we've got about 2 more steps and we're done. Minus 5 on the other side becomes plus 5. I'm going to put that 25 in parentheses so that I know that we're taking the natural log of only the 25. And then I would need to divide both sides by 8. And then notice that does get the x by itself. So there is your answer. That is the exact answer. And then if I want the approximate solution, I'm going to need to pull up my handy-dandy calculator and input that. That's going to be the natural log of 25 plus 5 all over 8, and rounded to 3 decimal places, 1.027. Next, number 11. We have another equation we need to solve. This is a logarithmic equation. Natural log, remember, means log base e. So I'm going to rewrite that as log base e so I can maybe get a better idea of what the next step might be. Square root of 2x plus 7 equals 3.14. Okay, now, if I have a log equation, I can convert to exponential. So if I bring the base down, switch the other two around, I'm going to have e to the 3.14 equals square root of 2x plus 7. Notice what I've done is I've gotten rid of the logarithmic equation, and now I have a square root equation. And the square root is isolated, so to get rid of the square root, I'm going to need to square. But that means I'm going to need to square both sides. Remember, when you have an exponent raised to another exponent, that's when you multiply. And that would give me e to the 6.28 equals 2x plus 7. And I've got a couple more steps and I'm done. Okay, so I'm going to recopy this. 2x plus 7 equals e to the 6.28. Moving the plus 7 over is going to make that minus. And then I would need to divide both sides by 2 and give the exact value. That is it right there. If I do any other calculation, that would no longer be exact. Okay, so this is the exact answer. Then if I want the approximate answer rounded to 3 decimal places, I am going to need to use the calculator. Okay, again, so we have a fraction, and to get the e to the, that is shift LN, 6.28 minus 7 all over 2, and to 3 decimal places, 263.394. And that's going to do it for problem number 11. Next, number 12. We need to solve this equation, give the exact value or values, so there may be more than one answer. Not sure yet. Notice that this is a logarithmic equation and we have 2 logarithms. So what we're going to have to do in this case is get our logarithms on the same side of the equation so that we can combine them using the properties of logarithms. I'm going to bring the negative log over. That's going to give me log base 4 of x minus 3. That will become plus log base 4 x plus 57 equals, and the 4 is now over there by itself. Now, according to the properties of logarithms, we know that if we're adding 2 logs with the same base, we can use the product rule, and the two logs become 1, and their stuff gets timesed. And once you have this simplified into a single log, you can convert to exponential. So we're going to bring the base down, switch the other two around. That's going to be 4 to the 4th equals, and then this is going to need to be FOILed. Here we go, x times x, and then x times 57. On the inside, we have a negative 3x. Last but not least, negative 3 times 57, negative 171. And then notice that my logarithmic equation has now become quadratic, so I need to set it equal to 0. Bringing the 4 to the 4th over is going to make that a minus 4 to the 4th, 256. And that's going to give me x squared, 57 minus 3 plus 54x, negative 171 minus 256 is negative 427. And then if you want to try to factor that, you can. I think what I'm going to do, since my b is even and a is 1, I think I'm going to use completing the square. All right, so if I recopy this problem up here where I've got a little bit more room, that's going to give me x squared plus 54x plus, and then what I'm going to do is move the constant over. Remember, that is the first step when you complete the square, which will make that a positive 427. And then I need to complete the square. Half of 54 is 27, and then 27 squared is 729 that I need to add to both sides. And then if you look at this new trinomial, that's going to factor as a perfect square trinomial. That would be the square root of x squared, which is x. We're going to take this sign, which is plus, and the square root of 729, which was 27. On the other side, I'm going to need to know what is 427 plus 729, 1156. And then taking the square root of both sides, we're going to get x plus 27 equals, that's going to be plus or minus the square root of 1156, which is nice. Nice. A whole number, 34. Moving the 27 over is going to give me x equal negative 27 plus 34, and x equal negative 27 minus 34. We're going to get two answers. Negative 27 plus 34, that gives me an x value of 7. And negative 27 minus 34 is negative 61. And I believe that the negative 61 is not going to be a valid solution. We need to check that, okay? I don't feel good about that. So taking that all the way back up to the original problem, if I replace x with negative 61, notice that's going to give me log base 4 of negative 61 minus 3, which would make me take the log of a negative number, which is not possible. So the negative 61 is not a valid solution, and so I believe the 7 is going to be the only valid solution. Checking the 7, log base 4 of 7 minus 3, equals 4 minus log base 4 of 7 plus 57. 7 minus 3 is 4. Log base 4 of 4 is 1. 7 plus 57 is 64. 64 is 4 cubed. And here we can see that the bases will cancel, so that will leave me a 3. 4 minus 3 is 1, and so the 7 checks out. Next, number 13. We need to express y as a function of x. And here they tell me the constant c is a positive number simply because you can't take the log of a negative number. They need to place that restriction on c. So if I'm going to express y as a function of x, that basically means I need to get y by itself. And if you notice, y is inside of the natural log, and so somehow I'm going to have to free him from his log cabin. So the first step here would be to move the natural log of c to the other side, giving us natural log of y minus 7 minus natural log of c equals negative 3x. And now with the properties of logarithms, I can combine my two natural logs into one. The subtraction indicates the quotient rule. So remember, a subtraction turns into a fraction, and whoever is first goes on top, equals negative 3x. Remember that natural log is log base e of y minus 7 over c equals negative 3x. And why did I do that? Because now it's time to convert to an exponential. We're going to bring the base down, switch the other two around, and notice that that gets the y out of the logarithm. And now with a couple more steps, I can isolate the y. Multiplying both sides by c to eliminate the fraction is going to give me y minus 7 equals c e to the negative 3x. And bringing the negative 7 over makes it a plus 7. And so now we can express y as a function of x. C e to the negative 3x plus 7. Next, number 14. Find the exact value of the trigonometric functions of theta. We are given this generic ordered pair, x and y. Notice it does not state that it's on the unit circle, so we would need to calculate the radius to determine if it is or is not on the unit circle. And when we write these exact values, if the denominator needs to be rationalized, we need to do that. So first things first, we need to calculate r using the Pythagorean theorem. X squared plus y squared equals r squared. Negative 4 squared plus negative 7 squared equals 16 plus 49, which is 65. That is r squared. And then if I take the square root of both sides, we can see that r is the square root of 65, which doesn't square root nicely, and it also won't break down into simpler radical form. So there is our radius. Now you're going to need to know the ratios for sine, cosine, and tangent. If you're not in the unit circle, sine is y over r, which in this case would be negative 7 over square root of 65, which needs to be rationalized, giving us negative 7 square root of 65 over 65. Cosine is x over r, which in this case would be negative 4 over square root of 65, which also needs to be rationalized. Negative 4 square root of 65 all over 65. And tangent is y over x, negative 7 over negative 4. And to simplify, a negative over a negative makes a positive. Next, number 15, find the exact value of the trigonometric functions. Here we want sine and cosine. We are given that tangent is negative 3/8. Remember that tangent is y over x. And we're also given that our angle is in quadrant 4. So if we draw a quadrant 4 angle, that would indicate that the x value should be positive and the y value should be negative. So now we know that it is the y that gets the negative. So that would be negative 3 over 8. And then we can solve for r. Here we go, using the Pythagorean theorem again. X squared plus y squared equals r squared. We're going to have 8 squared plus negative 3 squared equals 64 plus 9, which is 73. And taking the square root of both sides, we can see that 73 is in simplest radical form. So sine of theta, sine is y over r, which remember y was negative 3. Also, in quadrant 4, we know that sine has a negative value. So that's going to be negative 3 over square root of 73, which needs to be rationalized. Negative 3 square root of 73 all over 73. And cosine would be x over r. X is 8. And we know in quadrant 4 that cosine is positive. So we should get a positive fraction. And here it needs to be rationalized. 8 square root of 73 over 73. And we're done. Number 16, we want the amplitude, period, and the phase shift. And we need to graph. So the amplitude comes from the lead coefficient, which is always positive. The period for sine or cosine is 2 pi over b. B is the coefficient of x, which would be 2 pi over 4, which reduces to pi over 2. And the phase shift, negative c over b, where c is the constant part of the angle, that would be negative pi over 2 all over 4, which is the same as negative pi over 2 divided by 4. If we do the keep change flip, negative pi over 2 times 1 over 4 gives us a phase shift of negative pi over 8. So then to sketch the graph, there are 6 steps to the technique that I teach. Step number 1, starting point. And since we have a sine function, we know that sine starts at the origin. Step number 2 is the phase shift. And we do have a negative phase shift, so that ordered pair that we plotted at the origin is going to have to shift over. If this is a half, this is a fourth, which means this would be an eighth. So the phase shift is going to get scooted pi over 8 to the left since it's negative. Next, step number 3 is the wavelength. So then you need to ask yourself, how many eighths make a half? Well, an eighth and an eighth is 2 eighths, which is a fourth. 3 eighths, 4 eighths. Do you see this would be 4 eighths, which reduces to half? So how many eighths does it take to travel the distance of the wavelength, which is the period, it's going to take 4 of those. Here we go. 1, 2, 3, 4. And so this would be our end point right there. Step number 4, we need 4 spaces. I've got them. 1, 2, 3, 4. Step number 5, lay out your points. Notice that the original coefficient of the trig function was negative. And so that means that at the first hash mark, we're going to be at -6. Okay, so let's call this -2, -4, -6. We'll call that -6. And then we're going to return to the x-axis. 2, 4, 6. That would be +6 here. And then we return to the x-axis. And so then you can see that we have our nice, smooth sine wave. And that would be 1 period of the graph. Notice it says graph at least 2 periods. So that's super easy. If you can get the first period, you just go another 1, 2, 3, 4, and you continue to lay out your points. 1, 2, 3, 4. And you have another wavelength. Okay, so again, some of these important points to notice. This right here, this is pi/8 negative. So this would be positive pi/8. This next point would be 2 pi/8, which is pi/4. 3 pi/8. This would be 4 pi/8. Notice it reduces to half. So I feel pretty good about the way I've labeled these hash marks and laid out my points. Oh, step number 6 was to connect the dots, which we did. Next, number 17, find the period of the function, graph the function, and then we need to write the domain in set notation and the range in interval notation. We know that for secant and cosecant, the period is also 2 pi/b. We know that b is the coefficient of x, so that would be 2 pi/6. And if I rewrite that, that would be 2 pi divided by 1/6. Doing the keep, change, flip would give me 2 pi times 6/1, which is 6. And that's going to give me a wavelength of 12 pi. That is my period. Now, in order to graph 2 periods, the first thing we're going to do is we're going to remember that cosecant is related to sine, and sine starts at the origin. So we're going to put a dot at the origin because what we're going to do is lay out our points based on a sine function, and at the very end, before we connect the dots, we'll convert to the cosecant. Okay, so again, the 6 steps to do the sine function would be starting point. Sine starts at the origin. Step number 2 is phase shift. Notice we don't have a value of c, so there is no phase shift, but you have to consider that. Step number 3 is the wavelength, which is the period. So what I'm going to do is I'm going to change this pi/2, and I'm going to make that 6 pi. So 6 pi and 6 pi would make this 12 pi. And then I know from start to finish, I would travel a distance of 12 pi. Do you see sometimes you have to change the way the graph is labeled so that your graph is going to fit on there nicely. Step number 4, I've got to have 4 spaces. I've got them. 1, 2, 3, 4 spaces from start to finish. Step number 5, lay out your points. Sine starts at the origin. And since the lead coefficient was positive, that means that I would go up to positive 2 first, and then back to the x-axis, and then to negative 2, and then back to the x-axis. Now, if this were a sine function, we would connect the dots and make a sine wave, but it is a cosecant, so that's where step number 6 deviates. We're going to turn every x-intercept into an asymptote, and the other points are going to be our points for our curves. So we're going to have an up curve up here and a down curve down here. An up and a down together, that makes one period, one wavelength. If I need another period, I'm simply going to continue this pattern, and you can do it left or right. It doesn't matter which way you go, but I'm going to have another up curve here and another down curve here. Notice the symmetry. That completes the 2 periods of the graph. And with these asymptotes labeled, that's going to help me answer the domain question. Notice that the domain is not all real numbers, because everywhere there's an asymptote, that is an x value that must be eliminated. So in set notation, we're going to say the domain is the set of all x such that x cannot be, and then we're going to have to figure out how to calculate that. So notice our asymptotes go 6 pi, 12 pi. The next one would be at 18 pi. So that appears to be multiples of 6 pi. So to do that, you're going to say 6 pi k, where k is an integer. So notice integers would be -1, 0, 1, 2, 3, so on and so forth, both directions. And if I plug in a few values, notice if k is 0, 0 times 6 pi is 0, and that does give me an asymptote at the y-axis. And then if k is 1, 6 pi times 1 is 6 pi, 2 times 6 pi is 12 pi, so on and so forth. And that is giving me the asymptotes. Therefore, I know that this must be the correct way to write the domain, because the x's cannot exist at the asymptotes, which are multiples of 6 pi. Now, for the range, we know that the range is going to go down to -infinity for these lower curves, up to -2, and that is included. Do you see that from these bottom curves? The range, the graph is going to go to -infinity, but it's going to max out at -2, and then between -2 and 2, the graph does not exist. So we're going to do a union. We're going to skip all of the numbers between -2 and 2. We're going to pick up at 2 and keep going to infinity to account for the curves above. So here the range is -infinity to -2. -2 is included, together with everything from 2 to infinity. That is the range in interval notation. Next, number 18. Again, we're going to need to find the period. We're going to need to sketch the graph and write the domain and range. Now, for a tangent or a cotangent, the period is pi over b. B is the coefficient of x, so that would be pi over 2, and that is simplified completely. And then we're going to sketch the graph, knowing that tangent has consecutive asymptotes from -pi over 2 to theta to pi over 2, where our theta is 2x. So we're going to replace theta with 2x, we're going to need to multiply through by a half in order to get rid of the coefficient of x. So that's going to give us negative pi over 4. The half and the 2 are going to cancel, leaving me x. And the pi over 4, this gives me a pair of consecutive asymptotes. So, pair of asymptotes at negative pi over 4 and pi over 4, and I'm going to keep the graph labeled the way it is because it appears that it's going to be nice. Y'all do see if this is negative half, then half of that would be negative fourth. So that's why I put the asymptote where I did. That is step number 1 for graphing a tangent function, is to lay out your pair of consecutive asymptotes. Step number 2 says that you're going to have an x-intercept halfway between the asymptotes as long as there is no vertical shift, and we can see that there is no number added outside of the angle, outside of the trig function, so therefore there is no vertical shift, so the x-intercept will be halfway between the asymptotes. Step number 3 says at the first and third quarters, you're going to be at negative a and a respectively. So here a is 4. At the first quarter, I'm going to be at negative 4. And let's go ahead and call this first hash mark negative 4. At the first quarter, we're at negative 4. And then at the third quarter, we're at positive 4. And then step number 4 says connect the dots. And so we're going to get a nice smooth squiggle through those points approaching the asymptotes. That would be 1 period of the function. To get another period, you just write another asymptote and lay out 3 more points. An x-intercept, and then at the first quarter, negative 4, at the third quarter, positive 4. And that's going to get us another period. Now, the asymptotes, those were at negative pi over 4 and pi over 4. And then what would be this asymptote? Well, if we count, that would be 1/4, 2/4. This would be at 3 pi over 4. And then you can see that everything lines up because pi is 4 pi over 4, which would be the next hash mark. So everything seems to be lining up nicely. And notice if I wanted to do another asymptote, the distance here, 3/4, 4/4, this would be at 5 pi over 4. So I just wanted to show you a few of those locations for asymptotes. That's going to be handy when we write the domain. So in set notation, the domain are going to be the values of x such that x cannot be wherever the asymptotes are. Notice that the asymptotes appear to be at odd multiples of pi over 4. So how would I write that? I would say pi over 4 times k, where k is an odd integer. Now, check me. If k is an odd number, an odd integer basically means you can have negative or positive odd numbers. If k is 1, 1 times pi over 4 is pi over 4. The next odd number would be 3, which would give me the next asymptote. And so this is the way you would write the domain in set notation, specifying what your k is a multiple of odd integers. The range is super easy because our curves are unbroken. The curves do not have any point of discontinuity going from bottom to top, and so the range would be minus infinity to infinity. That is all real numbers in interval notation. Next, number 19, we need to find the exact value of this expression. The first thing you need to notice is that an inverse trig function is an angle. So we're going to bring this over to the side and work on it. Theta is the inverse tangent of 2/5. If I bring the inverse tangent back to the other side, that will turn it into regular tangent. Regular tangent is 2/5, but we know tangent is y over x. So that gives me the values of x and y. Now, what was I looking for? I was looking for secant of theta. We know that secant is the reciprocal of cosine. So if cosine is x over r, secant would be r over x. Notice that I do need r. And so the next step would be to use the Pythagorean theorem in order to calculate the value of r. Plugging in for x, that's going to give us 5 squared plus 2 squared equals r squared. 25 plus 4 is 29. And then if I take the square root of both sides, that tells me that r is the square root of 29, which is in simplest radical form. And I can finally answer the question they asked me. What is the secant of theta? It is square root of 29 over 5. Next problem, number 20. Solve the equation on the interval from 0 to 2 pi. They want me to express the solutions in radians, and I need to give the exact values. Now, the first thing I notice is that this trigonometric equation appears to be quadratic-like. So the first thing I'm going to do is set it equal to 0 and go from there. Now at this point, some people would do a substitution to replace cosine of theta with like x or something. I'm not going to do that. I'm just going to work with the trig function. I do notice that this is a quadratic. It is like 2x squared plus x minus 1. And we're going to try to solve that by factoring. Now, I have a method called the 3R method for a trinomial with a lead coefficient that I'm going to demonstrate. First R, we're going to remove the 2. And when we remove the 2, what we do with it is multiply it by the constant. That turns this into a standard trinomial, which I can then factor. If I read the signs, those are going to be different. To make cosine squared, that would be cosine theta and cosine theta. Numbers that multiply to make 2, that subtract to make 1, would be 2 and 1. Now, once we have the quadratic factored, remember we're doing the 3R method, so the first R I said was remove. Now the second R is replace. Notice the 2 I took off. I now have to replace it in front of each cosine. And then the third R is reduce. So I can reduce the first factor by 2. Getting those 2's to cancel is going to leave me cosine theta plus 1. In the second set of parentheses, 2 and 1 won't reduce, so that'll leave me 2 cosine theta minus 1. And that completes the 3R method, and now I can set each factor equal to 0 and solve. So cosine theta plus 1 equals 0, moving the 1 over tells me that cosine theta equals negative 1. Remember that cosine in the unit circle is x. So I need to find all values of theta in the unit circle that have an x coordinate of negative 1. And that's going to correspond to 180 degrees, which is pi. So my first answer that I get from my first factor is pi. Now, from my second factor, 2 cosine theta minus 1 equal to 0. Moving the 1 makes it positive. And if I divide both sides by 2 to isolate the trig function, we can see that cosine theta equals 1/2. And so then you're going to have to go to your unit circle and find all of the x coordinates that have a value of positive half. And according to the unit circle, the first theta, the first angle with an x coordinate of positive half is pi over 3. And the other angle with an x coordinate of positive half is at 5 pi over 3. And notice that those angles do have to be within the range of values specified from 0 to 2 pi. Those are all of the solutions of this equation. Next problem, prove the following equation. List any identities at the step where they were used. So to prove the equation means, in this case, we're going to work on the left-hand side of the equation, manipulating it so that it equals the right-hand side. And here I've got fractions that are being subtracted. And the first thing I realize is that in order to put these fractions into a single fraction, in order to subtract the fractions, I'm going to need a common denominator. Now, these denominators are completely different. So to get a common denominator, I'm going to need to multiply each one by the other one. For the first fraction, we're going to have tangent of theta times 1 minus secant of theta. That will be the denominator. Notice I multiplied the denominator by 1 minus secant theta. Therefore, I would need to multiply the numerator by 1 minus secant theta. And that would be something times itself, which would give me 1 minus secant theta quantity squared. Minus, in the second fraction, again having the common denominator of tangent times 1 minus secant theta, here I would need to multiply that denominator by tangent, which means I would also need to multiply the numerator by tangent of theta, and that would give me tangent squared theta. Anything times itself is that thing squared. And remember, eventually this is going to have to equal to 2 cotangent theta. Now that I have a common denominator, I can rewrite the fractions as a single fraction. And this right here is going to need to be multiplied. So I'm going to express that as 1 minus secant theta times itself minus tangent squared theta all over the common denominator of tangent theta 1 minus secant theta. And you do not have to keep writing this on the right-hand side. Now for the FOIL method. 1 times 1 is 1. 1 times anything is itself. So we're going to get negative secant theta. Same on the inside, negative secant theta. Last but not least, negative times a negative makes a positive. Secant theta times itself would be secant theta squared, and then minus tangent theta squared all over the common denominator. Now, have I used any identities yet? The first step that I did was algebra, so I didn't incorporate any trig identities. The next step, again, was just math, and the third step was the FOIL method, so I've not incorporated any trigonometric identities yet. At this point, though, I do see that I have a trigonometric identity that I can incorporate. I'm going to be able to replace secant squared theta minus tangent squared theta. That is one of our Pythagorean identities, and that equals to 1. So we're going to combine like terms, and we're going to replace what's in my brackets with 1 using a Pythagorean identity. All right, here we go. 1 minus 2 secant theta plus 1 all over my common denominator. And I don't know if you noticed, but this is simplifying rather nicely. And I did label the Pythagorean identity in the step here that I used it. Again, I'm going to need to combine like terms. 1 plus 1 gives me a 2. 2 minus 2 secant of theta all over my common denominator, which I do have to keep writing. And I'm about out of room, but that's okay because I'm about out of steps. Notice now that the two terms in the numerator have a common factor of 2 that I can factor out, leaving me 1 minus secant theta all over the common denominator of, and I just noticed that I had stopped writing my theta, which is a no-no. So I went back and filled in my thetas where I had stopped writing tangent of theta. And now at this step, we have a common factor that we can reduce out. The 1 minus secant thetas will cancel. And we know that 1 over tangent is cotangent. So from this step to this step, we're going to use a reciprocal identity. Because 1 over tangent theta is cotangent theta. And notice that that now equals the right-hand side of 2 cotangent theta. And we're done with the trigonometric proof. And that does it for our Precalculus Practice Midterm Review. If you have any questions or comments about anything that I've covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.